Now let's check out the solutions quickly. The language of the first question is a little bit tricky, but still the question is quite simple. The system with provided transfer function is placed in a unity negative feedback so that the transfer function becomes the feed forward transfer function of newly arranged system. We also know the steady state error is equal to 1 divided by static velocity error coefficient, and we can easily find the static velocity error coefficient, which will come out to be equal to 2. After that, we can easily find the value of steady state error, which will come out to be equal to 0.5. The next question is also mathematically quite simple, but you have to be a little bit cautious about what the question is actually asking you to find. The thing is, we generally apply the Routh-Hardis criteria on the denominator, but here we are supposed to find the zeros rather than poles of the system. So here we will apply the Routh-Hardis criteria on the numerator of the transfer function. And after forming the Routh array, we will get there are no sign changes, which means that all the zeros of the transfer function lie in the left half of S-plane. Now let's come to the next question. This question is actually a very good question. For LTI systems, we know that due to the additivity property of the linear systems, the output is equal to summation of different inputs along with their respective transfer functions. In this question, since we have to find the output corresponding to step disturbance signal only, we can assume the input signal is actually equal to 0. Using the Mason's-Grain formula, we can also find the transfer function, which will come out to be equal to 1 divided by s raised to the power n minus 2 multiplied by s plus 1. And we also know the transfer function is equal to Laplace transform of the output divided by Laplace transform of the input, which in our case is the disturbance signal. We can find the steady state output, but for this output to be equal to 0, we have to make sure that the exponential power of s in the denominator, which is n minus 2, must not be positive, because if that happens, then the steady state output will tend to infinity rather than 0. So the coefficient of s, which is n minus 2, should be negative. We will find that maximum allowable value of n is equal to 1. This question was actually a very good question, but unfortunately this question was incomplete, as there is nowhere written that the provided system is a LTI system. An undergraduate student may not be able to understand the importance of this term because in their syllabus only LTI systems are present. So most of the times they themselves assume that the system is an LTI system. As a matter of fact, whatever we have studied so far are all meant for linear time invariant system. Now let's see the next question. This question is also very simple. The expression for steady state error is present in the question itself. You have to simply convert this expression in frequency domain, and after finding the transfer function and putting the value in the expression of steady state error, you will get the value to be equal to k minus 1 divided by k. Before moving forward, let us discuss a very important confusion zone. Few of you may think that we should use static error coefficients here, but in the lectures also it is clearly mentioned that the static error coefficients which we are studying here are meant for only unity feedback systems. In the disadvantages of static error coefficients also, it is clearly mentioned that the analysis for non-unity feedback systems is quite lengthy and non-beneficial. That's why we do not use static error coefficients for non-unity feedback systems. After converting a non-unity feedback system into a unity feedback system, there are further few more steps that one has to follow to find the steady state error. And because of all these extra steps, the use of static error coefficients becomes meaningless when the system is having a non-unity feedback configuration. Moral of the story is, don't use static error coefficients for a non-unity feedback configuration. You will definitely get wrong answer. I have not taught you the concept actually. As per me, it does not make any sense to learn 1000 methods to solve a single problem. It will increase the burden of the syllabus on your head and will eventually lead to a lot of confusion in the exams. So it is better to learn easy and efficient methods and have good command over them. I don't think any of you can say that the provided solution for the question is difficult. Now let's see the next question. This question is very simple, but the only reason few students may find it difficult is lack of questions based on graphical analysis of the second order control systems. We have seen in the lectures also that the radius of the circle, which is the locus of the poles of the underlying system, is actually equal to natural frequency, which in our case is given to be equal to 2. So, the radius of the circle is allowed to be greater than or equal to 2. Similarly, the value of theta should be smaller than 60. In other words, we can also say that cos theta is greater than cos 60. And we also know cos theta is nothing but the damping ratio zeta. So, finally we get that the value of zeta should be greater than or equal to 1 by 2. So, the correct option is the first option. Let's come to the next question, which is a very simple question. After forming the root array, you will see that there are two sign changes, which means that there are two zeros of the polynomial which lie on the right half S-plane. The next question is also very simple, but the question actually checks whether the fundamentals of the concept are clear to students or not. The thing is, the definition of error is slightly changed in this question. So, the students who simply learn the formulas will not be able to solve this question. Generally, the error is equal to input minus output, but here in this question, the error is defined as output minus input. Otherwise, this question is very simple and you will get the value of steady state error to be equal to 1. Now let's come to the next question, which is not difficult but quite lengthy. We are provided with the function gs and cs, multiplying which we will get the feed-forward transfer function, and from that we can find the expression of characteristic equation. Our next step should be to form the root array to find which values of k permits the system to be stable. And as we know, for the system to be stable, all the elements of the first column of the root array should have the same sign. Since the first element is 1 which is positive, all the other elements should be positive also. The second expression is a little bit lengthy, but still you should be able to recall the concept of solving the linear inequalities. After solving all the three linear inequalities, you will get the common solution of k to be greater than 0 so that all the elements have the same sign and the system will be stable. Now let's see the last question, which is quite simple. We already know for sinusoidal input signals, the amplitude of the steady state output is equal to the amplitude of the input multiplied by the amplitude of the transfer function at the input angular frequency, which is 1 in this case. We can easily find the magnitude of the transfer function at angular frequency 1 radian per second coming out to be equal to 1 by root 2. After multiplying this with the amplitude of input signal, which is root 2, we will get the value of amplitude of the steady state output to be equal to 1.